Hello Jams! Welcome to ACE series. In this video, we are going to discuss previous year BITSAT questions from the chapter of work, power, energy or work, energy, power. Okay, so let me just brief you about ACE series if you are new to this channel. So ACE series is a series of videos specially made for BITSAT 2021 aspirants. Here we have a discussion on previous year BITSAT questions. Okay, so if you have missed the previous videos, go check out the description box, and if you haven't, let's begin. Okay, so the rules are quite simple. We begin with easy questions first, then we go to the moderate ones, and from moderate to more moderate questions, right, as usual. Okay, and rule number 2, whenever you have a question over here, you are supposed to pause the video and give that question a humble try. Okay, so let's begin. So question 1 over here, two bodies stick and move together after collision. So it is nothing but, by definition, it will be perfectly inelastic collision, right? Two bodies stick and move together after collision. In and perfectly inelastic collision, the two objects undergoing collision after collision moves together, right? So it was something like a definition type question, okay, asked in 2007. Very simple question. Okay, you can also watch it this way, that coefficient of restitution has a value 0 for perfectly inelastic collision. Okay, from here we can say that velocity of separation is 0. Okay, I'm just explaining it in detail, not needed actually. Okay, so velocity of separation is 0 means that the two objects undergoing collision will not be separated, or the two objects undergoing collision will move together, right? So simply the answer is perfectly inelastic collision. Coming to question 2, to determine power of an automobile, which of the physical quantities do we need? Okay, so now how is power defined? Power is rate of doing work, right? Or work done, average power will be work done in a given time interval. Okay, so where can we find that in the options? Here, option D, right? Work done and time taken for it. So that is how we can compute power of an automobile or any other thing. Okay, so we just need the work done and the time taken for it. Okay, since it's a single correct type question, in BITSAT you have single correct type questions, no need to check the other options, right? So let's move to other questions. Okay, the difficulty will keep on increasing, don't worry. So this question was repeated in 2006 and again in 2012. Okay, over to the next question. Okay, question 3 over here. It's quite an old question from BITSAT 2005. In this question, you have a potential energy versus position curve, okay, of an object. You are supposed to find the position of stable equilibrium. Okay, so first condition for equilibrium is del u by del x should be 0, right? Or we can say that slope of this graph, slope of the given graph should be 0 for equilibrium. Okay, so you can see that at x1, if you draw a tangent, the tangent is not parallel to the x-axis. Even at x2, if you see, the tangent is not parallel to the x-axis. So both of these options, x1 and x2, are out of consideration, right? They are not the position of equilibrium. Okay, if you see x3 has a slope 0, right? This tangent is parallel to the x-axis, so this condition is satisfied. So can we say that x3 is a position of stable equilibrium? No, there is condition 2 as well, right? This is the condition for equilibrium. This is the condition for equilibrium. For stable equilibrium, what is the condition? U should be minimum, right? The potential energy should be minimum for stable equilibrium. And in this case, you can see that the potential energy here is maximum, right? So this can't be a position of stable equilibrium too. The correct choice is D. Okay, here the potential energy is maximum. This is a position of unstable equilibrium. Okay, you can also verify it by looking at the second derivative. The second derivative will be the slope of the immediate next point. Okay, you can see that it is negative, right? The slope is negative, so this is maximum. Potential energy is maximum, and it is unstable equilibrium, not stable equilibrium. Okay, so none of the above is the correct choice. Okay, again option D. Okay, let's go to the next question now. Okay, question 4 over here on the board. It's from BITSAT 2018. In this question, you have two masses m1 and m2. m1 is initially moving with velocity v, m2 is initially at rest. Okay, so after some time there is a collision between the two. m1 gets embedded into m2 after the collision, and they move together as a system with velocity v dash. Okay, so basically you can see an inelastic collision happening over there. Okay, so you are supposed to comment on that v dash. Okay, velocity of the system will increase, decrease, remains constant, or becomes zero. Increase basically means v dash greater than v, decrease v dash less than v, remains constant v becomes zero, v dash equal to zero. Okay, so the best way to approach this question would be conservation of momentum, right? Because we can see a collision happening over there. So in any type of collision, momentum is always conserved, right? So let's just apply momentum conservation. So m1 into v, initial momentum, equals to m1 plus m2 into v dash. Okay, so since we have to comment on v dash, let's make that a subject. So that will give us m1 upon m1 plus m2 into v, right? So basically you can see that this value m1 upon m1 plus m2 will be less than 1, right? Of course the numerator m1 is obviously less than m1 plus m2, right? m1 is less than m1 plus m2, which means that this will be a proper fraction and its value will be less than 1. Okay, so you have to multiply v with a number less than 1 so that you get v dash. I repeat that, you have to multiply v with a number less than 1 so that you get v dash. So this basically implies that v is greater than v dash, right? So just an example for those who didn't get this. Okay, so v dash, let's take a number less than 1, let's take half. Okay, so you have to make v half so that it becomes equal to v dash, right? You have to make v half so that it becomes equal to v dash. So obviously v is greater. Okay, so v is greater, and we can conclude this, right? V is greater than v dash. Okay, so from there v is greater than v dash means velocity of the system decreases. V is greater, right? Initial velocity greater than the velocity of the system, velocity decreases. So yeah, that option B will be the correct choice, right? Let's move to the next question now. So next question, question 5 over here. In this question, you have a lift moving up with a velocity v. In that lift, you have an inclined plane. On that inclined plane, you have a block of mass m. Okay. Now, it is given that the block is at rest relative to the incline. So relative to the incline, the block is not moving. Of course, there is some frictional force which is avoiding the block from sliding down. Okay. So you are supposed to find the work done by the frictional force after time t. Okay, the way I am going to do this question is by just applying the definition of work, which is work equals Fd cos theta, right? So frictional force into displacement into cos theta, right? So let's find the frictional force. So we can draw the free body diagram first. Okay, so down the incline, suppose this is the block, down the incline we'll have mg sin theta. Okay, and up the incline will have the frictional force which is avoiding the block from sliding down. Okay, so these two forces will be equal, right? Because the block is at rest, so these two forces are equal. Okay, so F equals mg sin theta. So we found out the frictional force. Now let's go for the displacement. But the block is at rest, sir. Relative to the incline, the block is at rest. But if you see it from ground, the lift is moving. So the block along with the incline will go up. Right, the lift has some velocity, and if you watch it from ground, the block along with the incline is going up, right? So there is some displacement. So after time t, the displacement is due to the lift. Okay, so displacement will be velocity into time t, right? That will be the displacement after time t. So velocity into time t. Okay, so so the block along with the incline will move a distance vt in the upward direction, right? It will move a distance vt in the upward direction. Now you want to find theta. Let's name it alpha since we have used theta over here. Okay, So you have to find alpha, which is the angle between these two, right? The frictional force and the displacement. So what I am going to do is I'm just going to draw a normal to the surface, normal to the incline. Okay, I've just drawn a normal to the incline. So you can see that this angle will be theta, right? Since it is the angle between normal to the surface and normal to the ground, right? Normal to the ground and normal to the incline will make the same angle as the angle of inclination. I repeat that, normal to the ground and normal to the inclination will make the same angle as the angle of inclination. Okay, so this angle is theta, and you can see that alpha plus uh, theta plus alpha will be equal to 90 degree. Okay, the normal, the direction of the normal is this way, and the frictional force is along the incline. This is perpendicular to incline, this is along the incline. Okay, so theta plus alpha is 90 degrees. So we have to find alpha, which is 90 minus theta, right? So alpha is 90 minus theta. Substitute all the values over here, you will get your answer. Okay, so this is mg sine theta into Vt into cos of, okay, I'll write that over here, cos of 90 minus theta. Okay, so mgvt, cos of 90 minus theta is nothing but sine theta. Cos of 90 minus theta is sine theta, a little bit of math. And so sine theta into sine theta, sine square theta. So you have your answer. It is option B, right? mgvt sine square theta. Let's go to the next question. So question 6 over here is from BITSAT 2010. Very simple question. Okay, so in this question you have a spring. In the first experiment you are just going to extend that spring by 2 centimeters. You report its potential energy to be V. V is some value. Okay. In the second experiment you take the same spring. Now you extend it by 10 centimeters. What will be its potential energy? Very simple, right? Because we know that potential energy is given by half K delta x square, or basically you can see that potential energy for the same spring will be proportional to delta x square. Okay, so first of all we have increased the extension, right? From 2 we have made, in the second experiment we have made it 10. Okay, so potential energy should increase, right? So option A and option B get out of the way, right? Potential energy should increase. Now let's find it out. Let's take the ratio. So U1, potential energy in the first case, divided by potential energy in the second case will be delta x1 by delta x2 the whole square. Okay, by taking the ratio I got rid of the proportionality constant. Okay, U1 is nothing but V, right? Our potential energy in the first case is V. U2 we have to find, so let's take it to the other side, and V. So delta x2 upon delta x1 the whole square. Okay, so delta x2 is 10 centimeters, so 10 by 2 the whole square, so that will give you U2. So this will be 5 square. U2 is 5 square into V, which is 25V. Okay, very simple question from BITSAT 2010. We just cracked it. Okay, so let's move to the next question now. So next question, question 7 from BITSAT 2017. In this question, there are two balls, one with mass m, other one with mass 2m. The one with mass m is moving with velocity 2v in the I cap direction. The other one with mass 2m is moving with velocity v in the j cap direction. Okay, after some time they undergo perfectly inelastic collision, which means they will hug each other and move together, right? Stick to each other and move together with velocity v bar. Okay, so you have to find the percentage loss in kinetic energy. Now those who are new to this type of questions of percentage loss and percentage gain, you have to use this formula. Okay, so percentage loss will be given by change in the kinetic energy by initial kinetic energy into 100%. Okay, so in general percentage loss or percentage gain is given by change divided by the initial physical quantity into 100%. In this case we have kinetic energy. So change in kinetic energy, final kinetic energy minus initial kinetic energy upon initial kinetic energy into 100%. Okay, So first of all, we need to find this V, right? Why? Because we want final kinetic energy, right? So let's find that V. How will we do that? Conservation of momentum. So initial momentum 2mv I cap plus 2mv j cap will give us, now this moves together as a system, so 3m, 2m plus m, 3m and into v bar. Okay, so we have to find that v bar. First of all, we can cancel this m's, okay, and we'll get 2v by 3 I cap plus 2v by 3 j cap. Okay, now we are interested in the magnitude since we want the kinetic energy. This will be the final velocity, right, or the final speed magnitude, right? So 2v by 3, it will be 2v by 3 into root 2, 2v by 3 into root 2. Okay, a root 2, right, magnitude. You can use the formula anyways. So you have the final velocity, you have you can find the initial kinetic energy, so we can use that formula, right? So first of all, let's find final kinetic energy. That will be half m is 2m plus m. Okay, pay attention over here. M is finally in our final condition, the finally what is happening, these two masses are moving together, so m is nothing but 2m plus m. Okay, so kinetic energy final is half 3m into v square. So this square, final velocity square, so that will be 8v square by 9. Okay, 8v square by 9. So that will give us this will be 4 and this will be 3. So 4 mv square by 3. Okay, this is the final kinetic energy. The initial kinetic energy is very easy to find. So first of all, half mv square, half m into 2v square, which is 4v square, okay, plus half m, now m is 2m, 2m into v square again. So here we'll get mv square and here we have 2mv square. So 2mv square plus mv square, 2mv square plus mv square, 3mv square. Okay, so you can note it down till here. Let's use that formula. Now just we have to use that formula and get our answer, right? So let's just do that. Okay, so change in kinetic energy, final kinetic energy 4mv square by 3 minus initial kinetic energy 3mv square upon initial kinetic energy, which is again 3mv square into 100%. Okay, so you can cancel this mv square, mv square, mv square throughout, and you will get 4 by 3 into 3 minus 3 3s are 9. That will be minus. So that minus sign shows that there is loss in kinetic energy. Okay, final kinetic energy is less than initial kinetic energy. There is loss in kinetic energy. Okay, so it is depicted by that minus sign. So minus 5 upon 9 into 100%. Okay, whatever percent we get. Let's see. So 9 by 5, I think it will be 55.55, right? 0.5 are 45, again 5 are 45, yeah. Okay, so it is 55.55. We can round it up to 56. Okay, so it was a good question from 2017. Okay, I hope the idea is clear. Now let's move to the next question. You can rewind the video and watch it again if this question is not clear to you. Okay, so let's move to the next question now. Question 8, it's an old BITSAT question. Okay, again it's very similar to the previous question. Again you have two masses, each of 10 kgs. Now each of them is moving with a speed of 5 meters per second. This velocity is in the direction I cap and this velocity of the other ball is in the direction of j cap. Okay, you are supposed to find the velocity, okay, the velocity or the speed after collision. Okay, they move together after collision. It is given that they move together after collision. So again, perfectly in elastic collision, right? So all we have to do is just conserve momentum. So initial momentum 10 into 550 I cap plus here 10 into 550 j cap, right, will be equal to the final momentum. Now this two will move together as a system. The final diagram will be somewhat like this: 10 kg, 10 kg. They move together with velocity v bar. Okay, and the final momentum will be 20 into v bar. Okay, so we have to find that v bar and find its magnitude. Okay, so it will be 5 by 2 I cap plus 5 by 2 j cap. Again, as I said, AA will be A root 2. So 5 by 2, the magnitude will be 5 by 2 into root 2, which is nothing but, it's given over here, 5 by root 2. Right? You can split 2 as root 2 into root 2. Why am I telling this? Okay. So the answer will be C. Okay. Very, very simple question. Okay. So let's go to the next question now. Okay, question 9 over here, it's from BITSAT 2008, again an old BITSAT question. So in this question, you have dropped a ball from a height of 10 meters, okay, from the ground. After bouncing on collision with the ground, the ball loses 40% of its initial energy, okay. So now it rises back to some height h dash. Of course, it won't be equal to 10 meters, right? Because it has lost some energy during collision, okay. So it rises to some height h dash. You are supposed to find that h dash, okay. So how will you do this? Energy conservation won't work here, I guess, okay. So actually there are no principles as such which you can apply in this question, but you can do it by pure logic, okay. First of all, we'll say mgh, okay. Conservation of mechanical energy won't work, but conservation of energy will work. I'll show you, okay. So mgh minus, so I'm deducting this 40%. 40% will be 40 by 100, right? mgh, the energy at this point, initial energy, minus 40% of the initial energy equal to mgh dash. Is this correct? Initial energy minus 40% of the initial energy will be equal to the energy at this point, right? We accounted for the energy which is lost, okay. So this is correct. Conservation of energy works. Conservation of mechanical energy won't work, unfortunately, okay. So mg will get cancelled throughout. So you can see that h minus 0.4 into h, that will give you h dash. So 0.6 into h will be h dash. Or you could have also seen it this way, that it will rise up with 60% of the initial energy, right? So 60% of mgh, 60% of mgh will give you mgh dash. So mg cancels mg, and here you'll have 0.6. So 0.6 h equals h dash, okay. Anyways, so you'll get your answer over here, 0.6 into 10, 0.6 into 10, which is 6 meters, okay. So logic. So let's move to the next question now. Question 10 from 2010, you guessed it, it's from conservative forces, right? So potential energy is given as a function of x and y. You are supposed to find the force vector. Quite a simple question. You have to find the force vector at 0, pi by 4, okay. So how will you do it? First of all, you'll find fx using minus del u by del x. Then you'll find fy, which is minus del u by del y. Then you'll bring them under one roof, right? fx I cap plus fy j cap. So this will be our force vector, right? So I hope you know to do this. This is partial differentiation. Whenever you're now keep one thing in mind, whenever you are doing partial differentiation, whenever it is with respect to x, x will treat y as a constant, okay. Whenever it is with respect to x, x will treat y as constant. In the similar fashion, whenever it is with respect to y, y will treat x as a constant, okay. So one variable treats other as a constant. So that's why partial differentiation, okay. So anyways, let's do that. So differentiation of cos of x plus y, so this minus sign, and differentiation of this will be minus sine x plus y. Then again we have to differentiate this. So differentiation of x with respect to x is 1, and differentiation of y will be 0 because it's a constant for x, right? So again you have 1 plus 0 into 1 plus 0, so into 1, right? So that doesn't matter. you have sine x plus y. Okay, so now substitute this value. Okay, so you'll have sine 0 plus pi by 4, sine of pi by 4, which is 1 by root 2. Okay, now let's do it for f of fy. Okay, force in y direction. Again, differentiate this, you get the same thing. Okay, minus sine x plus y. Okay, just I'll do that extra step for those who didn't understand. So again, I'm going to differentiate this right now with respect to y. So x is a constant, so differentiation of x with respect to y, since x is a constant, I'll take it, the differentiation will be 0, and for y it will be 1. So basically 0 plus 1 is a 1, so 1 into this, the same thing, right? So that's why I didn't write it over there. So the answer is again the same thing. So again, substitute the values and you'll get the answer to be 1 by root 2. So you are going to compile it under this roof, one roof. Okay, so 1 by root 2 I cap plus 1 by root 2 j cap. This is fy, this is fx, right? So 1 by root 2 I cap plus 1 by root 2 j cap, 1 by root 2 I cap plus 1 by root 2 j cap. Option B is the correct choice. Let's go to the next question. Okay, question 11 over here is from BITSAT 2015. Now in this question you have a spring of natural length L, and now you can see those springs. Okay, so first you extend it by a distance x, okay, and then you again further extend it by a distance y. Okay, so you do it stepwise. First step you just extend it by distance x, and then you further extend it by distance y. Okay, so you have to find the work done in second stretching. Now catch the point over here. Okay, so this becomes our initial condition, this will be our final condition, because we want to find the work done in this stretching. This is our second stretching, this is our first stretching. Okay, this is first stretching, this is second stretching. We want the work done in this process. Okay, initial condition over here, final condition over here. Some of you might have considered this as the condition, right? And that will give you the wrong answer. It will give you option D, which is of course the wrong answer. Okay, so the point over here is they want the work done in this process. This is the initial condition and this is the final condition. This is the second stretching, first stretching, second stretching, right? So let's find that out. So how will we do that? So basically work done is nothing but negative change in the potential energy, right? So work done is nothing but negative change in the potential energy. So work done will be change in potential energy is final minus initial. So negative of that, initial minus final, right? So basically solving now. So initial potential energy will be initial condition over here now. Okay, pay attention. So half k x square, or L plus x the whole square. No, L is the natural length, right? X is the extension. Okay, so x square, right? Okay, so don't get confused by the question. So again, half k, now it will be finally we have what is the length extended. This is x plus y, right? So extended length is x plus y the whole square. Okay, so we have to just find this, just compute this. So it will be half k x square minus half k x square minus half k y square minus half 2k x into y. I just opened this up, x square y square plus 2 xy. Okay, and then open the brackets. So you can see that this and this will get cancelled, and from there you can take minus half common. Okay, since half is common in each of the options. Okay, so here we'll get and k is also common, so half minus half k we took common, so we are left with y. Y also we can take common. Okay, let's take half ky minus half ky common, so we are left with y plus 2x. Okay, this is gone, minus half ky is gone, so we are left with x plus y plus 2x. Okay, so the correct option will be half ky 2x plus y. The negative sign basically shows that the work done will be negative, right? work done is against the spring force. Okay, spring force is in this direction, and the extension work and displacement basically are in the opposite direction. Okay, so the work done is negative, but basically they want the magnitude. Okay, so that will be our answer. So over to the next question now. Question 12 from 2013. Now you can see the composition among topics, right? Pulley system from laws of motion, and we are discussing it in work per energy, right? So here you have pulley system, one block has mass 0.36 kgs, other one has a mass of 0.72 kgs. Of course, this will have some acceleration in the downward direction being heavier. Now the system is left from rest, so this gets an acceleration A. The block A follows with the same acceleration. Okay. Now you are supposed to find the work done by string on block A after 1 second. Okay. Find the work done by string on block A after 1 second. We are going to approach this question by using the definition of work itself, which is work is force into displacement, right? So work done by string, right? Work done by string will be nothing but the work done will be due to the tension force, right? So tension force into displacement into cos theta. So one thing to note from here is that the displacement and the tension will be in the same direction, right? Displacement and the tension will be in the same direction. The angle between them is 0. So cos 0, 1. So TD. So we have to just find tension, displacement, multiply them, we get our work. Okay. So let's just do that. So apply Newton's laws now to find tension. So applying it to block 1, T minus 0.36 into G, T minus mg basically is equal to mass into acceleration. Net force is equal to mass into acceleration. Here we'll have 7.2, 0.72 into 10, and minus T, net force is equal to mass into acceleration. Okay, just add this two. So you'll get, what will you get? You'll get 7.2 minus 3.6, 3.6. This will give you 1.08, 70, 30 and 8. Yeah. So then acceleration will be 3.6 into 1 divided by 1.08 goes for 12. So this will be 0.3, 0.09. So 3 by 9. So 30 by 9. Okay. That will be 10 by 3. So acceleration is 10 by 3 meters per second square. Okay. So why did I find the acceleration? Anyways, you'll come to know. Let's go for tension now. So tension will be 0.36 into 10 by 3. So I'm using the first equation. Here you'll get 3.6 and here you can cancel it for 12, right? And you get minus 3.6 and here you'll have 1.2. So 3.6 plus 1.2, that will be 4.8. So 4.8 is the tension force. Now let's find the displacement. Okay, let's find the displacement. How will we find that? We know we have to find the displacement for 1 second. Okay, so ut plus half at square. U is 0. Initially the system was left from rest. So ut plus half at square. Ut is 0. That term is 0. So half a. That is the reason why I found out acceleration. I'm not a moron. Okay, so yeah. So half a t square. 1 second, right? So 5 by 3. So the displacement is 5 by 3 and into 4.8. So that will give us our work, right? So 3 1s are 3, 3 6 are 18, 16 5s are 80. So that will give us 8 joules is the correct answer. Okay, let's move to the next question. Yes. Question 13 from 2007. In this question, you have a mass m which is moving with velocity v. This mass will go and strike a block of mass capital M which is hanged to a ceiling with the help of a string. So now once it strikes the mass capital M, it gets embedded into it. They move together as a system. Okay. So and this height h is the maximum height achieved by them. Okay, so you are supposed to find the v, okay, the initial velocity with which the sphere began. Okay, so some of you might directly apply conservation of energy and will go wrong, okay, because you cannot conserve energy over here. Why can't you? Because here you can see an inelastic collision happening, right? The ball, the mass m is coming with velocity v, it strikes and it gets embedded into the capital M mass, and they move together. So inelastic collision is happening, and in inelastic collision, kinetic energy initial is greater than kinetic energy final. There is some loss of energy, right? So this velocity won't be v, this velocity will be some v dash, some different velocity, okay? There is some loss in kinetic energy, the speed will decrease. Remember, the speed of system decreases, okay? So first of all, let's find this v dash, and then we'll conserve the momentum, right? That is the best way we can do it, okay? So since we cannot see v dash over here, we'll find that v dash first, okay, and then conserve momentum in this case, okay? So we can conserve energy over here, okay, because here there is no collision, no non-conservative forces involved. So here we can conserve energy. So we can say half m plus m into v square. I'm conserving energy over here, not over the entire thing, okay, just over here, and the ball has struck the block of mass m, okay. So half mv square will be equal to mgh, right? It entirely gets converted into our potential energy. So m is m plus m, right? M plus m into gh. So what can we cancel? M plus m. So you'll see that v is nothing but root 2 gh. Was obvious, because if you see it rises a distance h, so the velocity will be under root 2 gh, right? Okay, anyways, so v dash, okay, sorry, this will be v dash, right? V dash is under root 2 gh. Okay, now we will conserve momentum. So initial momentum m into v is equal to final momentum, which is m plus m into v dash, okay, m plus m into v dash. So once we do that, what will we get? We have to find v, right? So we'll get m plus capital M upon m, and v dash is root 2 gh. Okay, so the correct choice will be m plus m upon m into root 2 gh. Option A is the correct choice. Okay, let's go to the next question now. I hope this one was clear. So we cannot directly conserve energy. We have to, you can see the inelastic collision happening over there. Okay, so first we applied conservation of energy only at this portion, and then we applied conservation of momentum. Momentum is conserved in any type of collision. Okay, no more talks. Over to the next question. So question 14 over here is from BITSAT 2011. Okay, so in this question you have dropped a mass of 0.1 kg from a height of 0.24 meters from a pen. Okay, this pen is massless, it is attached to a spring. So what will happen is that when you drop this, it will when you drop it, initial velocity 0, it will gain some velocity throughout its journey over here, and when it strikes that pen along with the spring will go down, right? Spring will get compressed. So potential energy over here gets converted into kinetic energy till here, and again when it strikes that pen, the kinetic energy of that ball will get converted into potential energy, and it will compress the spring. Okay, so the spring, when it is dropped from this height 0.24 meters, the spring is compressed by this amount, okay, 0.01 meter. You are supposed to find the height for which the compression will be 0.04 meters. Okay, so basically conservation of energy, right? Now let's apply conservation of energy over here. So mgh, the initial energy, will be equal to half kx square, and don't forget this, right? This is where we consider potential energy to be 0, okay, and this is some negative potential energy, right? So we have to account for that too, which will be mg, and this distance will be nothing but, I have shown it here, it will be x dash, right? Delta x dash, delta x, sorry, in this case it will be delta x. Okay, so now First of all, the one way, long way of doing it is to find this k through this equation, then go to the scenario 2, then use the same conservation of energy, substitute the value of k, and the only unknown there will be h dash. Okay, so that is a big method. What I will do is I'll just bring this mg delta x over here. So take mg common, h plus delta x, right? So we get half k, and this will be also delta x, right? The compression delta x square. So you can see that this m is constant, g is constant, k is constant in both the cases, right? In this case we are not changing the particle, the gravity won't change, of course the spring is not changed, so the spring constant won't change. So you can directly say that h plus delta x is directly proportional to x square. This is a shortcut way of doing it. Okay, so now let's take the ratio, its ratio with this one, right? So I'm just changing it with the other case. Okay, h with h dash, x with x dash, and delta x with delta x dash. Okay, so I'm going to take the ratio. So that's how I got rid of the proportionality constants, this constants over here. So h plus delta x upon h plus h dash plus delta x dash is equal to delta x upon delta x dash the whole square. So I hope this idea is clear. First we applied conservation of energy, just flip this term to the other side, and then we took it common. We realized that m is constant, g is constant in both the scenarios. M is going to remain constant, g will be constant, k will be constant. So this is directly proportional to that. Okay, so we took it from the other case also, right? And we took the ratio just to get rid of those proportionality constant. Okay, so now just substitute the values and you'll realize that only unknown is h dash. Okay, so h will be 0.24 plus extension in the first case 0.01, okay, upon h dash unknown. Extension in the second case should be equal to 0.04, and here you'll have 0.01 divided by 0.04 the whole square. Okay, so 1 by 4 the whole square, or 1 by 16, and here you'll have 0.25, which is divided by 0 h plus 0.04. Okay, so where can I do it now? I'll do it over here. Okay, you can quickly note that down if you are noting it down anyways. So 16, now 0.25 is nothing but 1 by 4 into 16, and you'll get h dash plus, so that will be h dash plus 0.04. so this will give you 4 minus 0.04, that will be h dash, and that will be nothing but 3.96 meters. Okay, so that's how you do it. One was the long way, you find the k value from here, then again apply conservation of energy in the second scenario, and then substitute the value, the same value of k. The only unknown in that equation will be h dash. Otherwise you do it this way. Very nice way, right? Over to the next question. The discussion on work energy power is incomplete without discussing the chain problems, right? So chain problem is over here. So the total length of this chain is L. It's placed on a smooth table. The mass is M. Okay, the L by nth portion of this chain is hanging. You are supposed to find the work done in pulling the chain back to the table. So work done in this process. Okay, so how will we do that? Work done in the process will be negative change in the potential energy, right? So let's consider this to be our reference line, where we'll consider potential energy to be 0. Potential energy is 0. So this is, you can see the final potential energy in this case will be 0. So negative change in potential energy means initial potential energy minus final. But change in potential energy is final minus initial. So negative of that, initial minus final. Final is 0, right? Final potential energy is 0. We have considered that as our reference line. So basically the work done will be the initial, whatever the initial potential energy is. Okay, so the initial potential energy will be due to this portion, right? So how will we find that? mgh. So m, it is not the total mass of the chain now, right? It is the mass of this portion, So since m has mass L, L by N will have a mass m by N. Okay, it is uniform. So if m has mass L, L by N will have mass m by N. So m by N G, of course, and into H. Now H, you have to locate. You can see the mass is spread out, right? This mass is spread out. It is not at a particular location. Okay, so you have to look for the center of mass, and where will that be? Over here, right? Half of this distance, half of this distance, half of L by N, and which is L by 2N. Half of this distance, you'll have the center of mass. So we can assume that entire mass of this hanging portion is located over there. So the height will be mgh will be L by 2N, right? The position of center of mass. So that will give us mgl by 2n square, and that will be our answer. Okay, quite easy, right? So I'll give you your homework problem, then some tips maybe, and then we'll wrap up the class. Okay, you can note this down if you want to. Also, the notes of this lecture are available on the website, links in the description. Okay. Question 16 over here, it's your homework question. It has appeared in BITSAT 2016. Okay, so in this question you have two masses. One is moving with initial velocity u, so they undergo perfectly elastic collision. Okay, and after that collision they separate out. One moves with v1 making an angle θ1 with respect to the horizontal. Other one moves with velocity v2 making an angle θ2 with respect to the horizontal. You are supposed to report the value of θ1 plus θ2. Okay, now this is a very standard question. It is also there in your NCERT, but do give it a try before looking it up over there. Okay, so yeah, so whatever result that you get in this question, you are supposed to by heart it in this format, that when two equal masses undergo perfectly elastic collision, their final velocity vectors make an angle of whatever answer you get. That will be the statement. Okay, I'll just repeat the statement. When two equal masses undergo perfectly elastic collision, their final velocity vectors make an angle of dash with respect to each other. Okay, so with that being said, let's wrap up for today's class. I hope you enjoyed it. Do share this video with somebody and help them in their BITSAT preparation. Also do follow the word series which is going on my Instagram. That will help you boost your score in the English section of your paper. Okay, I'll see you soon in the next class. Rather, you'll see me soon in the next class. Drop a like, subscribe, keep enjoying physics.